Okay, so let's talk about the demonstration with the meter stick. The impulse equation, super important equation. One thing I want to point out before we explain what's happening with the meter stick is that this is the second law. This impulse equation is the statement of the second law, but it introduces two new concepts or new properties that we can measure. One called the change in momentum, or just the momentum, and then the other one is the impulse. So you can think about how forces act on objects, but if you multiply the force times the time, we refer to that as the impulse. That tells you some other piece of information. It gives you something different than just telling you how much force was applied, or for example, what was the average force applied. In this particular example, one of the things I think we would all agree that did not change was the mass. The mass that I dropped. I never changed the string. I just slid the thing over, and when I let it fall, it was the same mass. So this guy stayed the same. That guy was constant. I would argue that since they fell the same distance, that the change in the velocity would also be the same. And the reason is because the amount of velocity that they get is based on how far they fell. The farther they fall, the faster they're going to be moving. But I let them fall the same distance before the string started to become tight. And at that point, because of the difference in the way they behaved, there was a difference in the way they changed the velocity. But the amount of velocity that they had before the string became tight, that's the same no matter no matter what part of the meter stick I drop it from, because the distance is the same. It's based on the length of the string that I tied. So I would argue that on this side, that this is a constant. That I don't have any control over the change in the momentum. But what I do have control over is the other side of the equation. And hopefully what you recognized was that the property that caused the string to break is the force. The more force you exert, there's some certain amount of force that when you exert that force, then you exceed the ability of the string, and then the string is going to break. And it's a pretty uniform thread, so it's pretty consistent throughout the length of the thread. So the difference then must be that there was greater force when I put the string closer to the clamp than it was when I put it on the far end, where there was a little more flexibility. Now, you saying that it was more flexible or that it was like cushioned it or something, that's fine. That's not an incorrect explanation. It's just that that's like a middle school explanation, right? I mean, that's not something that you need this equation to even talk about. You just say more cushioning. But what really happened is when you say cushioning, what cushioning means is reducing the force. That's what you really are talking about. But you're not really explaining why did the force go down. And in this case, if the product on the right side is a constant, and I have no control of the change in the momentum, I'm going to give these washers some momentum, and this meter stick is going to take them away. Then what I can do on the other side is by allowing this to flex downward, it increased the amount of time, and by increasing the amount of time, that decreased the amount of the force that was acting on it. So the impulse is perfectly demonstrated by this, that if you can extend the time over which you make a change in your momentum, the effect will be to decrease the force. So now if you just say increase the time to decrease the force, that's part of the answer. I mean, that's partial credit, but it's not really explaining, because look, if I push on the table for a short time, or I push on the table for much longer, I didn't change anything. Nothing happened there. The fact that I exerted that force for a longer period of time, it didn't have any effect on anything. So it's not like how long you exert a force on something always is always important. Okay, but when it would be important is when it involves a change in momentum. And in this case, it was involving a change in momentum, because we had the washers which were falling. The string was attempting to stop that from happening. It was attempting to change the momentum of the washers. And in one case, it was able to do it. And in the other case, it just could not do it. And the difference is it was the amount of time. The other demonstration that I would normally have you do, I'm going to have you do as a mental exercise. This is actually something that Newton did a lot, and also Einstein also did this a lot. Excuse me, it was thought experiments. So I'm going to have you just visualize this in your own head, and I feel like I can very accurately predict what's going to be the result of this experiment, and you can judge for yourself if I'm accurate. If I were to ask you to get on top of your dining room table and stand near the edge, and what I'm going to ask you to do is to just hop down off of the table. I would make a prediction about what's going to happen when you land. And when I'm telling you, I asked you to jump down off the table. That was the only instruction that I gave you. But I'd be willing to bet you that if I did that, if I asked you to jump down off the table, you would land like this. You would bend your knees, and you would also bend your hips a little bit. And I wouldn't have to tell you to do that. And I'd be willing to bet you that you've known that for almost your entire life, for literally your entire time that you can remember back to. There's never been a time that you did not know that if you jump down off something, that you want to bend your knees a little bit. It's just something that you learn by experience. I mean, some people are better at it than others, but everybody has some intuition that they've developed that they feel less pain if they bend their knees when they jump down. And the reason for that is exactly what the impulse equation says is going to happen. When you jump down off the table, you don't have any control over the amount of momentum you're going to give. That's a product of gravity. Gravity is going to increase your velocity. It's going to change your momentum. And when you land, you need to get rid of that momentum. Now, you can't determine how much momentum you can get rid of because that's based on your mass and how high you jumped from. But what you can do is on the other side of the equation is you have a lot of room to play. And so if you can increase the amount of time, which you're doing by bending your knees and bending your hips, the amount of time that it takes for you to make that momentum change, then that will reduce the amount of force. And the opposite is true also. So if you land with your legs straight, that's going to cause you to come to a stop much more rapidly. And as a result, that's going to decrease the time. And since this number on this side is still a fixed value, just like it was when you bent your knees, that means that the force is going to have to go in the opposite direction. So that's going to cause the force to increase. So there's a huge amount of conceptual questions that can be asked that just taking the second law and expanding it to create two new properties, one called the change in momentum and the other one called the impulse.